Good afternoon, ladies and gentlemen, esteemed colleagues and students. Welcome to this track 2 tutorial on HBM System and Architecture for AI Applications by Mr. Manish Jain and Mr. Nikhil Raghavendra Rao. I will I'll introduce the speakers briefly and then hand over to Mr. Jain. So Mr. Jain, over to you.
Hello everyone, welcome to this presentation. Today we are going to talk about HBM System and Architecture for AI Application. My name is Manish Jain, I am Senior Director at Rambus. Along with me today is Nikhil Rao, who is Principal Engineer Architecture. We'll have a question answer session in the end of this presentation. While during the presentation, if you have any questions, you can use chat box. Nikhil and I work in Rambus Interface IP Solutions team. Rambus provides wide range of high-speed interface IPs. We provide both controller IPs and the physical layer IPs. In today's talk, we will be focusing on high bandwidth memory solutions. In this presentation, we'll talk about how AI is defining requirements for memory bandwidth. We will introduce HBM DRAMs and show how it is evolved to keep pace with the memory bandwidth demands. We'll also show some product examples using HBM solutions. Then we'll deep dive in the HBM architecture. We'll learn about the HBM features and also learn about the features which are key for the AI. HBM system is 2.5D system. So we are trying to integrate SoC and DRAMs in one package. In order to do that, we need an interposer. And we'll also talk about interposer design and how it impacts. Before we conclude, we will talk about the signal integrity analysis, and this is important to keep the data rate at such high data rates. The world's digital data is growing exponentially. In fact, it is growing at a rate much faster than technology growth rates for processing, memory, and network. AI is increasingly needed to make sense of this growing amount of digital data. And this data in turn is needed to train and improve the performance of neural networks. We believe that this trend will continue in future. Training is growing 10x year over year. AI training workloads are demanding much higher bandwidth. Last year, training models surpassed 175 billion parameter requirement. Ongoing trend to move business applications to cloud is further helping in the AI growth. To satisfy this growth rate on AI training, we have increased hardware requirements. But it is not possible to keep increasing hardware. We need to look at efficient hardware solutions. And this is driving need for greater compute and memory efficiency. Interest in neural network was developed early on in 80s and 90s, but it never took off then. There were two main reasons. One was that compute was not fast enough and memory was not high performance and capacity was not enough. Because of these limitations, conventional approaches were performing much better. Today we have much better compute and we have much better memory performance and capacity. Now neural networks can outperform conventional algorithms. New ASICs are being built and these are demanding high bandwidth memories. This is creating demand for innovative memory solutions like 2.5D memories and 3D memories. We have been talking about training the neural network and inference. Let's quickly understand them. How is neural network trained? Large number of data examples and desired outputs are presented. Algorithm processes repeated examples and network is trained. It is a brute force and very compute intensive. Accuracy of outcome depends on the example set's quantity and the quality. Training can be long and it can take a couple of weeks. Coming to inference. Once the network is trained, it is used to process data which it has never seen before. Inference should be very fast and power efficient. AI solutions are present throughout the internet. AI requirements are different at different points in network. Let me talk about compute and memory requirements at cloud, edge, and endpoints. I will start at cloud. It has high performance AI training. We have the highest memory bandwidth requirement, typically greater than 1 terabyte per second. Here on-chip memory, HBM, GDR memories satisfy these requirements. At edge, requirement is high performance, low power training, and low power inferencing. Memory bandwidth required is around 500 Mbps. We have seen all type of DRAMs are used here. At endpoints, it is basically low power inference. Memory bandwidth required is 100 Mbps. GDR and LPDDR memories are used here. In this slide, we will discuss about the common memory systems. Let's start with the DDR. DDR has been used for a long while, and it is most prevalent memory system. You would have seen its usage in servers, PC, laptops. It has also been used in automotive extensively. It is very cost efficient, and also you can increase the memory capacity by adding more slots. So this provides that flexibility. DDR4 tops at 3.2 gigabit per second per pin, while the DDR5 memories are going 6.4 gigabit per second per pin and beyond. Next, I will talk about low power DDR, LPDDR. As the name suggests, it is low power. So it was primarily conceived for the mobile application and widely used in the mobile application. It has similar bandwidth like the DDR, and it is also finding its usage in automotive and also in AI edge inference. Next, I will cover out the graphics DDR. Graphics DDR, as the name suggests, was originated for the graphics system. It runs at very high data rate. The current generation GDR6 runs at 16 gigabit per second per pin and beyond. This provides a very good trade-off for bandwidth, cost, and reliability. Apart from graphics, it is also used in AI inference, networking, and automotive. Next, I am going to cover about HBM. HBM is high bandwidth memory. This system is very different than the previous three memory systems which we have talked about. Here inside one package we have the SoC and all the memories, DRAMs mounted. For instance, in this picture we have 4 DRAMs mounted inside the same package along with the SoC over the interposer. This per line runs at similar data rate like DDR, which is 3.2 Gbps for the HBM2E and 6.4 gigabit per second per pin for HBM3 and beyond that. The difference here is it is a wide I/O kind of interface. So it has 1024 lines compared to the previous systems which we have discussed, which has 16 or 32 lines. This provides a much higher bandwidth within a small form factor, and it provides much higher memory density because it has stacks of high bandwidth memory in the same package. There are several advantages of this system. I will deep dive on this system in this presentation. This HBM finds its application in high performance compute, AI training, network. HBM is a 2.5D system. It consists of SoC, DRAM, and interposer all mounted within one package. DRAM is basically DRAM cores, So there is a stack of DRAM cores. You can have up to 12 DRAM core stack. Bottom we have a base die in the DRAM. The DRAM base die is attached to the interposer through micro bumps. So DRAM base die would have micro bump, and interposer top side would also have micro bumps. Some of the interposer signals will directly go to the BGA to like the power supplies for the DRAM or certain other signals. The DRAM PHY signal will communicate with the HBM controller PHY or the system on chip PHY through the interposer. So this is really a very wide bus. It has 1024 data signals, but there are several other control, command and address signals which communicate between the DRAM and the HBM. The system on chip die will also have micro bumps, and they will hook up with the micro bumps on the interposer. The bottom side of the interposer will be C4 bumps, and those will be mounted on the package substrate like a regular 2D connections in a 2D package. Here I am showing one system of HBM3 where we have a SoC and 4 DRAMs, and all these are mounted over an interposer and hooked up. So the basic thing which we see here is it provides a very small footprint for a very large bandwidth memory and very low power memory. HBM was originally developed for graphics, but now the HBM memory is finding its use in many other applications like AI, HPC and networking. HBM memory bandwidth has been increasing over the years. HBM initial version had 1 gigabit per second per pin. It was doubled in 2016 in HBM2, where the per pin rate increased to 2 gigabit per second, and the overall bandwidth provided by the DRAM was 256 gigabyte per second. HBM2E was released in 2018. It was an enhanced version of HBM2, and it nearly doubled the bandwidth. Last year, HBM3 has been announced. The I/O speed is going to be higher than 5.2 gigabit per second per pin, and we see this trend of growing speed is going to continue. HBM3 will eventually clock much higher data rates, and our estimate is that it would provide 1 terabyte per second of bandwidth per device. AI training typically requires greater than terabyte per second memory bandwidth. In this slide, we will look at number of devices required to meet this 1 terabyte per second bandwidth. Looking at various DRAM generations, it required 4 DRAM devices of HBM2 type to meet the terabyte per second mark. HBM2E also required 4 devices to meet this mark, but towards the end of HBM2E, we are seeing even 2 devices can come very close to the terabyte per second mark. Going forward, HBM3, 2 devices would definitely cross the terabyte per second mark. If we use a 4 devices in system, we could get greater than 3 terabyte per second system memory bandwidth. This is really very encouraging, and if you look at this, all the characteristics, very high bandwidth, very low power due to the 2.5D system, and very high memory density, this provides a lot of advantage in AI training applications where we are really looking for very high system bandwidth. Here is examples of HBM used in accelerator card for AI training solutions. 2 devices of HBM2 provided 512 gigabyte per second bandwidth in the first generation solution. In the second generation solution, there were 4 devices of HBM2E type used, and it provided a system memory bandwidth of 1.8 terabyte per second. On the silicon interposer, there were 4 DRAMs mounted, of 4 HBM2 DRAMs mounted, and ASIC was mounted. This was all packaged inside one small footprint package. Here are a couple examples of AI inference solution. Looking at memory used, we see two choices. One uses two HBM2 devices to get half terabyte per second system bandwidth and 16 GB of capacity, while the other uses 8 GDR6 DRAM device to get the similar bandwidth and capacity. So far we have reviewed the benefit offered by HBM in AI applications. We have seen HBM memory solution examples for training and inference applications. It is time to look at HBM architecture. I would hand over to Nikhil to discuss HBM architecture.
To understand the HBM architecture, let us first have a look at the HBM memory subsystem. So the HBM memory subsystem consists of a memory controller, a PHY, the interposer which connects the PHY to the DRAM, and of course the HBM DRAM. So the HBM memory controller is connected to the GPU CPU infrastructure where the actual AI application runs, and the AI application or the GPU is connected through an AXI interface to the memory controller. The controller then connects to a PHY, and the PHY is the one which actually interacts with the DRAM through the interposer. Now the memory controller and of course the AXI buses which connect to it are all soft IPs and are configurable. The PHY is usually a hardened IP and is provided in the GDS2 format. So overall the entire integration and the subsystem is going to look like this. So let us look at the key performance factors which make HBM suitable for AI applications. So firstly, it offers a very high bandwidth as the name suggests. It uses double data rate on both data and command address bus. The HBM2 generation went up to 450 Gbps, whereas the HBM3 is targeting 800 Gbps and even beyond that. Power is another factor. So in order to reduce power, a data bus inversion feature is available, which reduces the number of signal toggles that happen during data transfers. The power was further reduced in HBM3 by bringing down the I/O signaling voltage to 0.4 volts. The other very important thing that AI applications require is a lot of parallelism, and this is achieved in HBM using multiple channels. There were 8 channels in HBM, HBM2 and HBM2E. The latest generation HBM3 has now extended to 16 channels. There is also a concept of pseudo-channel which divides a single channel into 2 parts logically, and the number of banks and bank groups are provided so that multiple rows can be kept open, and it also allows multiple commands to be read off different banks. The capacity of the HBM DRAM is another key performance factor, and so far with the HBM3 generation the capacity has been raised to 32 gigabits using a 16 high device. The reliability of the HBM is also a key factor. Since there is an interposer between the PHY and the DRAM, it is important to maintain the reliability of the connectivity between the PHY and the DRAM. So that is achieved primarily by having an extra parity bit which goes on the address and also on the data, and the DRAM will check for this even parity whether it is maintained. If it has been maintained, then the DRAM accepts all the commands, otherwise it indicates an error back to the PHY or the controller saying that the parity is not maintained. Lane redundancy and remapping is another important method. In case a particular link is broken or a single address line is broken or a single data line is broken, then an extra lane is available which can be used as the address or the data line by doing a simple remapping. Loopback mode is another important feature inside the HBM DRAM which allows the PHY or the controller to test the timing related constraints, where it sends a burst of data which is applicable both to the address as well as the data bus, and the DRAM captures that data and the PHY or the controller can read back. Now this loopback mode does not use the primary memory core which is inside the DRAM. and rather uses flip-flops which are built into the DRAM, particularly for loopback support. There is also ECC support, where the DRAM has extra cells to store the ECC data and also extra signals to indicate ECC data. In the HBM3 generation, on-die ECC was also added inside the DRAM. So let us now look at the HBM DRAM organization. We will go generation by generation and first look at the first generation of HBM. In the first generation of HBM DRAMs, they were organized with A words and D words. Some of this architecture is still carried forward. The A word, D word is especially carried forward even in the future generations. The A word consisted of the command and the address, and the D word was used for data. And this also included some control signals which are used to qualify the data, and also included ECC or data mask data. There were 8 channels in the first generation of HBM DRAM, and each channel had 1 A word and 4 D words. So that made it 32-bit into 4 or a 128-bit data bus per channel. So this is what a single channel would look like, the A word in the center and D words 0, 1, 2, 3 organized. The burst length that was supported was 2. So a single burst could have 128-bit into 2, which would come to 32 bytes, which is typically a single cache line size. The DRAM is of course stacked, in the sense dies are stacked one above the other vertically, and up to an 8 high stack was supported in the first generation. The capacity of the DRAM would be up to 4 gigabits. There were 8 or 16 banks per channel, and they were organized into a possible maximum 4 bank groups. So the idea of banking actually helps in having multiple rows open, and the constraints between bank to bank transfers are also a bit relaxed, especially when you are going from one bank group to the other bank group. So this actually enhances the parallelism. There was a single command clock which is named as CK, and there were separate read and write data strobes. So the read strobe was to qualify the data during a read transaction, and write data strobe is sent by the PHY of the controller to qualify the data during a write transfer. So the second generation of high bandwidth memory were the HBM2 and HBM2E. So the wide I/O bus, which was used in the first generation of HBM, obviously provided higher bandwidth. In addition to that, the extension of the burst length to 4 made the bursts longer, and the fetch of data in a single burst was increased to 64 bytes. There was also increased capacity and density, and HBM2E has introduced a 12 high stack of DRAM. There was also a further need to increase the parallelism a little more. So the number of banks per channel has been extended to 48 banks. And the concept of pseudo-channel was introduced for more parallelism. So what happens in pseudo-channel is that the commands contain a pseudo-channel address bits, and the bank address is used to indicate which pseudo-channel is being accessed. The 4 D words are actually being split into groups of 2 D words each. So this would be a pseudo-channel 0, and this would be the pseudo-channel 1. The A word remains the same. The only difference for pseudo-channel addressing is that an extra bit in the bank address is used to indicate which pseudo-channel of data we need to fetch from. So that was the change done. Now how does this cause more parallelism? Now with each pseudo-channel, we can actually divide the data across 2 pseudo-channel D words. And the A word gives us the extra bit, which allows us to open extra rows. And since the burst length has been doubled, the same amount of data can be stored in one pseudo-channel itself. And of course, for backward compatibility, what was done is, in the case where a pseudo-channel is not enabled in the device, then it could still operate in the HBM1 mode for HBM legacy mode. So that was allowed in HBM generation 2. So now the third generation of high bandwidth memory has come out, and in the need to address more parallelism, the number of channels has been increased to 16. So that means there are 16 A words, right? The effective number of D words remains the same. What has been done is, instead of having 4 D words, per channel. Now there are only 2 DWords per channel. So this is only creating parallelism by giving more addresses, and that means more address space and more rows which can be kept open. So that means at any point of time about 2k rows of data can be activated using an active command. There are 64 banks per channel now, which again adds to more parallelism. There is no legacy mode now, it has to be only pseudo-channel mode. The data width remains the same, 1024. So the parallelism part has been addressed by increasing the number of channels and by having more banks per channel. Higher bandwidth and speed, of course the data rate is now going to reach up to 6.4 gigabits per second, and the burst length has been increased to 8. So now there are 32 bytes per burst, which is going to be the same per pseudo channel. And there is a higher capacity, so the DRAMs are now capable of stacking up to 32 gigabits, and the 16 high stack has been introduced. A pseudo channel is now a single D word. As we can see, the organization is like this. There is an A word in any given channel, and there are 2 D words, but they operate as pseudo channel. So since they operate as pseudo channel, only 1 D word of data is active at any point of time. Power reduction. So IO signaling has been reduced to 0.4, and a few changes in the clocking side. So the command clock and the write data strobe need synchronization, and the write strobe is now acting as a data clock. What has been done is the command clock runs faster than the data clock. So this way what happens is the power on the address side is reduced, whereas the data rate throughput on the data bus has been increased. And they have introduced on-die ECC to improve the reliability. Next thing to look at is the HBM signals and how they have evolved over different generations. So if you look at the data lines, first we'll see that there were 128 lines per channel. So all the signals listed here are per channel. So up to the HBM2E generation, we will note that there are 128 DQ lines per channel, whereas in the HBM3 it is now down to 64 per channel. That is definitely because the number of channels in HBM3 are now double of what they were up to HBM2E. There was a data masking feature wherein a data mask was also provided along with the data lines with the same timing as the data lines in order to mask a byte or some bytes of data. Now in HBM3 the need for this has been taken off, and therefore there is no masking allowed, primarily because we now have a single cache line size, and initially the data mask was considered of use because in typical CPUs you may want to avoid a read modify write, so you write only the bytes which are necessary. However, over time full cache line writes seemed more efficient, and therefore the data mask has been removed. The row command width has been increasing generation by generation consistently, and finally it has reached 10 lines for the row command. One of the reasons for this is because of the addressing, and the amount of addresses that need to be provided are increasing as the density of each device is increasing. The column width has more or less stayed the same. The idea is that the page size would not have increased significantly. However, there are a few other interesting points which we will cover shortly. The address parity lines were provided as part of the commands itself. So this was encoded into the row or column command up to the HBM2E generation. In HBM3, a separate parity signal has been introduced. So now this extra signal is again introduced as a way to increase the amount of reliability that the HBM3 generation will have. The data parity lines are now decreasing in HBM3 per channel, but they are the same if we consider 1 per D word. So the idea behind parity is that in case there is an even parity and any parity is missed due to a link error or a breakage in the links, then immediately the DRAM will signal that. ECC. So ECC was actually provided in the way that there was an extra signal which was a multiplex between the data mask. So it could be used either as a data mask or as the ECC. Now what has happened is that there is a need for it. Since the data mask has been removed, the need is to have a dedicated ECC. In addition to that, on-die ECC has been introduced from HBM3, which was not there in the previous generations. And the severity was not there in the old generations. This has been introduced in HBM3 to kind of indicate what type of error has been corrected or what type of error has been detected. So these are the differences in the signals that are seen from generation to generation. So a summary of how the various generations of HBM have evolved is depicted over here, and we can see that in the first generation, of course, the intention was to have a DDR kind of memory, separate write and data strokes. There was a capacity of up to 4 gigabit per channel. These capacities are per channel. A 4 high stacked DRAM was considered. The signaling voltage was at 1.2 volts. We had a burst length of 2. And then the next generation came, the speed had already doubled. The capacity has doubled. And the stacking also went all the way up to 8 high stack. And the introduction of burst length was 4. So from generation 1 to 2, we can see that the speed has increased, the capacity has increased, and also the throughput bandwidth in a way has increased. Also introducing the pseudo-channel mode is again another way of increasing the amount of parallelism. The next HBM2E generation has now gone all the way up to 3.6 Gbps and now accommodates a 12 high stack, which allows more capacity for devices. The bus lengths have all remained the same. Some extended addressing was there on column and row. Now with the new generation of HBM3 coming in around this calendar year, and possibly a little bit work in the previous year, the signaling voltage has been dropped in order to reduce the power. On-die ECC has been introduced to increase reliability. The clocking has been changed to allow the data clocking to be faster. The commands are thereby clocked at half the data rate, and the burst length has been doubled because the width of the data per channel has been cut in half. So to ensure that the fetch or the number of bytes fetched is same, the burst length has been increased. To have more parallelism, there are now 16 channels. So these are the available devices today, and it's quite clear that these DRAMs are targeted towards high performance computing, graphics, and definitely for AI applications. So let's briefly look at the commands that are there in HBM. So since the signaling separates row and column, so we have the ability to give row and column commands. So that also means that row and column commands can be given in parallel since they have separate buses. However, care should be taken not to have an activate followed by a read to the same bank address, and those kind of things have to be taken care. However, it allows for parallelism of commands as long as the bank addresses don't interfere. So these are the commands that are supported. You have an activation, which is to activate the word line, recharge to close the word line, refreshes for periodically refreshing the data. There's a power down mode and a self-refresh mode, which is quite similar to a couple of the other DRAM families as well. And of course, we have the no operation. Column commands are separated into read commands, write commands. Mode register is considered a part of the column command bus. This is just to improve the efficient usage of the column command bus. There is also an additional command known as refresh management, which has been added in HBM3. The purpose of this is to give some additional refreshes, especially when there is very high activity in the DRAM. So sometimes the data would be fetched or written to very frequently. So it may be a good idea to periodically close that row and give an additional refresh, make sure that the data is not lost. So this has been added as part of HBM3. So looking inside the HBM DRAMs to understand the clocking scheme, which was used in high bandwidth memory first generation, second generation, and up to 2E. So here this is a single clock where the clock is used to drive the command and address, and that is sampled with the CK. And this clock is a per channel clock, just like the command address bus as well as the data. This command clock is then rerouted back to form the read strobe, which is again source synchronous read strobe, and that is used to clock the data which is being read out from the DRAM. Similarly, during the write path, the write strobes are used to clock the data that is received from the host controller. So this is a very simplistic clocking scheme. the clock and the write strobes both run at the same frequency. Write and read strobes run at the same frequencies. So while moving into HBM3, the data rate that had to be met was much higher. So the plan is to go all the way up to 6.4 Gbps and perhaps even higher than that. So one of the key challenges was how fast can the command clock run? If the command clock has to be running for a 6.4 Gbps system, it has to run at 3.2 GHz, considering that the command bus is also double data rate. Now at the HBM2E generation, the speed was up to 3.6 Gbps, so the clock was at 1.8 GHz. Now with 6.4 Gbps, the challenge became to nearly double the clock frequency for the command bus. And again, the utilization of the command bus would not be as high as the data bus. So a simple method was formed where the command clock was decoupled from the data clock. And that is why the clock that is used per channel is primarily only for the command and address bus. The data is now clocked by the strobes. So the read and write strobes are the ones which will be used to clock the data, both on the write path as well as on the read path. Now the opportunity is available to make the write and read strobes to run at twice the frequency of the CK, which is what is happening in HBM3. So, but what happens because of this as a side effect is that the WDKs and the clock are no longer synchronous. Now the most important thing to note over here is the command clock was used to be retimed and sent out as the read strobe in the case of up to HBM2E generation. But now there is no connection between the command clock and the read strobe. So a clock is required. For that purpose, the write strobe itself is used for generating the read strobe on the return path. Now the first thing is that the write strobe and the clock have to be aligned. So an alignment training is required to make sure that they are not off by a very high value. So this is limited to within about 20% of the CK time. The read strobe is, as we can see here, retimed from the write strobes. And the important thing is, what it means is that if the write strobe is going to be retimed for a read path, that means the write strobe should also be generated during a read. So this is no longer acting like a strobe signal, but more acting like a data clock. So in order to meet the requirement that when there is a read command, the write strobe should be available so that it can be retimed and regenerated as a read strobe. What is required is you need to have a little bit of extra preamble. So what happens is in the writes, a 2-cycle preamble is enough because there is no need to regenerate the read strobe. Whereas in the case of a read, the write strobe has to be generated for 4 cycles before the actual read data is ready. So you have a 4-cycle write strobe preamble and a 2-cycle read strobe preamble. The postambles will be same. So this kind of new clocking structure was done. And in addition to that, a 4-phase divider was done so that the alignment of the write strobe and the CK can be done using a phase detector. So because if the write strobe is running at twice the frequency and clock is running at half the frequency, in order to check their alignment with a phase detector, you need to divide the write strobe. Now when you divide it, you also have to generate 4 phases so that you can phase detect and do a proper alignment between the clock and the write strobe. The reason why this alignment is required is because everything from the command bus, especially a read or a write, is also governed by a read and write latency. So the time when the write strobe is generated should now be aligned to the latency, but the latencies are always calculated in terms of the clock cycle or the command bus clock cycle. And that is the reason why it is important to have a fair alignment within some limit between the write strobe and the command clock. So the next thing to consider is how the pseudo-channel mode added to the parallelism in HBM2 generation and onwards from there. So first, when we consider the legacy mode, which was applicable to the first generation of HBM, the data bus was 128-bit wide and the entire 128-bit bus was used in a data fetch or write. So let's look at a read. These are 2 back-to-back reads shown, and after the read latency the data is available. The burst length was 2. So a total fetch of 32 bytes was done in each read. The important point to note also here is that while 2 activate commands are shown over here, there could be 2 different rows in different banks. So that allows data to be accessed where read goes to one bank and the next read goes to another bank. Now in the pseudo-channel mode, while looking at the illustration in the case of HBM3, where of course the data rate has been doubled and the burst length is now 8, but the total fetch per burst remains the same. It is still 32 bytes per read. So now the advantage here is that we can activate 2 rows in different pseudo-channels. And also we could read 2 rows from different pseudo-channels. And because there is no connection between one pseudo-channel to the other, there is a clear parallelism available. The reads can be given one after the other. So while one could think that in this case the data was 128 bits and it was fetched together, here with just one CK cycle delay, we can have fetching of data from 2 different rows. This is particularly suitable for AI applications where you are looking for 2 different data from 2 different pages, which are spaced apart in different rows. So after going over the parallelism features in high bandwidth memory, now we will look at reliability aspects. So for test and boundary scan, the IEEE 1500 standard has been adopted. This is a serial interface and the test clock can run up to 50 megahertz. So what happens here is this interface has the ability to shift in commands as well as shift in data when the command is for writing into a register, a WDR or a command register. So the choice of whether it's going to be an instruction command or data is decided by this select WIR signal. So instructions also include the channel number. So we can send commands to a specific channel or broadcast it to all the channels. And the readout is done on a serial out data port which comes out as an output from the DRAM. This is also per channel. And there are 2 instructions, xtest and xtest-rx, which are used for boundary scan. So how this works is when the DRAM is put in receive mode or xtest-rx mode, what happens is the host controller will be in boundary scan transmit mode. And using the 1500 command xtest-rx, we can set the DRAM to be in receive mode. The host controller will transmit static data and the DRAM will capture the values. Whatever value is captured can be read out through the 1500 interface. And then we can compare with what was transmitted. So this provides a reliability check to ensure that whatever was sent, there is a connectivity or a proper connectivity to the DRAM. Similarly, there is a case where the DRAM can be in the transmit mode and we can actually provide what data the DRAM has to drive on each pin. And that can be captured by the host controller when it is in a boundary scan receive mode. So overall, this gives a very good way of checking the connectivity between the controller and DRAM. So while there is a 1500 option for doing boundary scan check, we also need to consider the AC integrity, which means is there any problem with the link with regards to sending and receiving the signals at the intended speed bin. So what happens is there is a loopback feature available here where the DRAM will be put into a loopback mode. What that means is whatever is sent by the host controller at the desired speed bin will be captured by the DRAM. And this is captured by the registers which are placed inside the HBM DRAM's receivers or in the IO stage. So this does not involve the memory core array. So anything that is written into this will only be captured at the first stage IO buffers. And there is an option to use different kinds of patterns. So this works both ways as well. What goes from the controller is captured by the DRAM. There is also an option to make the DRAM generate some data which the host controller can capture and then check whether it is receiving the correct data. This is done using linear feedback shift register patterns. So these are not necessarily fixed patterns. While fixed patterns could also be used, there are also random patterns. So this kind of checks whether the link has good stability with respect to SI and other signal integrity aspects. So we have seen 2 methods to find out whether a link is broken or not. One is related to a physical connectivity check through DC and the other is through checking whether there is any lack of timing ability or the link is unable to run at the maximum speed possible. So what if there is a link broken? So if there is a link broken, then some redundant pins are provided both on the A word and the D word. So in the case of the first and second generation HBMs, there was a separate redundant pin for a row and a column. Now in the case of HBM3, there's only one provided for every A word. So either we could remap a column or a row. So how this remapping and redundancy works is, let us say a link is broken. For example, DQ0 in this case is broken. What can be done is the RD pin or the redundant pin for the data, which is 2 pins per D word and 1 per half D word, can be used as DQ0. And this remapping information can be told to the DRAM once again through the 1500 interface. And this uses an instruction known as lane repair, and this is sent through the 1500 interface. So once we tell that this lane is gone and broken, you can repair them. So in this table, if we look at the case where DQ0 has to be repaired, we are seeing that in the case of HBM3, DQ0 is not used in this case. DQ0 appears on 1, 2 appears on 1, and the extra redundant pin would now act as the data bus inversion pin. So this is how the lane repair would happen in case DQ0 is broken. Now there are two kinds of lane repairs. One is soft and one is hard. So soft lane repair will be cleared whenever the power is taken off. However, the hard lane repair works like a fuse. So you can burn the fuse and make the links fixed based on whatever repair has been determined. So why both are provided is, first we can use soft lane repair to find out which lane is broken, and then use hard lane repair to make it permanent. So continuing with more reliability aspects, ECC was also there right from the first generation of HBM. There was a slight difference between the first, second, and coming to the third generation. So first to second generation 2E had ECC bits where there were additional cells inside the DRAM to store the ECC data. But there was no on-die ECC. The host controller was responsible for computing the ECC, and those ECC bits were transmitted as instead of the data mask bits. So either you could use it as a data mask or you could send ECC data, but both could not be used. In the HBM3, what has been done is, since the data mask is completely removed, the extra bits that were there would be used only for ECC data, and also on top of that, on-die ECC has been introduced. Now, this is a symbol-based ECC. Size and the method to be used are specific left to the DRAM vendors on what they will choose to use. And whenever there is an ECC error detected, it will be corrected or detected. That information is provided back with extra 2 bits of severity signal, which tells whether there was a single bit error corrected, multiple bits errors were corrected, or there is an error which cannot be corrected. And also when there is a refresh all banks, some automated on-die ECC error scrubbing was done. So this covers some important aspects of reliability. So we have now covered the reliability aspect as well as the performance aspect where parallelism has been introduced. This covers and sums up the architecture part for the high bandwidth memories.
Interposer is an important component of HBM memory system design. It is base of 2.5D integration. We'll now discuss about key considerations for the interposer design. Interposer serves as a medium to connect ASIC to the DRAM. It also provides the power path for the chips on the system to the package substrate. Designing interposer requires a couple of steps. Channel SI simulations are performed and to keep an eye on the voltage and timing budget. Power integrity checks have to be done to keep a check on the noise targets. A careful layout review will help reduce number of iterations and also will help to achieve the highest data rate. HBM memory technology is doubling I/O speeds in each generation. Interposer technology is keeping pace with this by taking steps to improve on the signal and power integrity aspects. Here I am comparing silicon interposer for HBM2 and HBM3. While in HBM2, the design used 3 or 4 metal layers to connect between the DRAM and the ASIC. In HBM3, there are greater than 5 layers available. Thick metal layers and thick dielectric layers are also available. These provide lower insertion loss and reduce crosstalk. In the silicon interposer, we also have a provision to add silicon decaps. which will help in supply decoupling and thus improving the power integrity. In both the technologies, there are few considerations which has to be followed. Signal layer routing width and spacing are guided by the DRAM bump pitches, micro bump pitches. And one of the important thing we need to consider while designing this is to take care of the ground shielding layers and ground metal width optimization. We have already reviewed the HBM memory system components. Now we will take a look at the HBM system signal and power integrity. Signal and power integrity analysis is important to achieve the high bandwidth. Timing budgeting is an important step here. We need to budget the timing for each components and meet it. There are several trainings supported by PHY and DRAM. This helps us to calibrate and achieve good voltage and timing margins, but we need to consider the residual errors and non-linearity of training components in our system budget. Overall, this is a exercise which involves all the components of the memory system, the PHY, the interposer, and the DRAM. We are going to talk about system signal integrity and power integrity analysis. Let's start with the channel simulations. For the channel simulation, we need to model all the components. We use the IBIS models for DRAM and the PHY. Interposer extracted models are used. This is very critical step here. We need to have a good interposer extraction. It should capture crosstalk, it should capture various other impacts. And in the simulations, we can have components like random jitter, crosstalk, PSIJ enabled. Once we have all this available, we can set up the test bench, and we can use various standard tools for the simulation. We suggest to do the bit error rate analysis, and the objective in the end is to meet the DRAM and PHY IMASC requirements. The next step is on the power supply noise simulations. Here we again need accurate modeling of package and interposer supply network. We need the CPM models for SoC and the DRAM. We then run the simulation with the current profiles and analyze the impact of interposer package and on the ID caps. So this is an iterative process, and we can optimize the power peaking with the on die cap and package cap and the interposer caps. The goal in the end is to meet the power supply AC noise budgets.
So to summarize, it's quite clear that the AI ML is now driving a complete renaissance and a complete revolution in the computer architecture. A lot of new silicon is being designed to cater to these needs. In all these applications, memory bandwidth becomes very, very crucial. And these requirements are coming from the fact that training data that is used to train AI ML networks requires high bandwidth as well as high capacity. As of today, HBM2E is one of the preferred solutions, and HBM DRAM is moving aggressively to meet all kinds of demands that the AI ML industry is posing. HBM3 is going to be probably the futuristic leader and the one which will be of choice with its high bandwidth and parallelism, which will be used by AI and ML applications.
This concludes the prepared presentation. We are now happy to take any questions on this topic.
Thanks, Manish and Nikhil, for a very enlightening tutorial. I think you had given a really good brief from where we have really started with the DDRs, and then you've explained an evolution of HBM over the generations and how we are decoupling the clock from it and enabling and increasing the the data rate, right? I'm pretty sure that our user base and participants would have a lot learned from you, right? We have few questions for you to answer with. The first one is like, is the increase in the bandwidth of HBM is primarily due to the miniaturization of transistors? If so, on what technology node HBM3 speed of 1 terabytes per second is achievable? I mean, it is fundamentally whether the technology is giving that speed or it is in protocol, right? I believe it's both. I mean, maybe you're an expert who can help answer better, please.
Yeah, that's a very thought-provoking question. Is it basically technology or is it other things, right? So,
Yeah.
as you said, the answer is both. And we highlighted in the presentation that it's an entire system which has to work, right? So, what has come up is a couple of advances in the training, which has been come in the HBM3. For example, the command address was reduced to half data rate because to enable the data rates to go double. So, but still we can run command address signal integrity at much lower data rate, right? So there have been advances in trainings like the training algorithms for voltage reference because this is a single-ended design. And the other thing is there have been a lot of improvement in the interposer design technology. So as this 2.5D technology is used in HBM and also in many other chiplets and all, there have been a lot of work going on in this, and the interposer technology is also improving. So it's a overall combination of things. Provided the base, we have got the base support from the miniaturization of getting a smaller transistor and running at higher speed, but that's not the sole thing. The second question of part of this question is tricky. So the DRAMs are still in development. I don't want to comment on that, but on the controller side, normal, you don't need any specific process. It is available in it can be done in 7 nanometer, 5 nanometer, those kind of processes.
Yeah, I think it's ever hungry, data hungry world, right? I think whatever that we feed would not be sufficient. I think HBM3 would solve most of the problems, I believe. Okay, so with that, I'll go to the second question we have in the Q&A. Does the on-die ECC means that the ECC calculation and checking happens on the die itself, or so the question is, where does the ECC really happens? Yeah.
Okay, so I'll take that question. Yes, it is part of the the DRAM itself. So there is an ECC engine which is built in. So like we have talked about so many multi-channels and all that. So you saw that the ECC signaling is all per channel. So that also means that there is going to be an ECC engine per channel again. So the idea is that different vendors are using different techno schemes for doing the ECC. The ECC algorithm is kind of like open. And it's a symbol-based ECC, what has been thought of. So there are some algorithms which can do single as well as multi-bit error correction. So yeah, it's all getting inside the DRAM now. So the need for reliability has pushed this particular scheme.
Right. Right. Okay, great. So I have a question for both of you folks, right? So because HBM is something like any A or H devices would really want it to because of the bandwidth reasons, right, and the memory that it could allow it. But at the same time, the cost of the HBM certainly goes high because of the interposers, right, in 2.5D. So, and whereas if you see, there are certain attempts on the die-to-die interfaces are going towards the organic nature. Do you see that, in the future consortium of HBM will look after, using this organic package as one of the mediums in the near terms or maybe in the future terms to optimize the cost of the HBMs?
Yes. So I know that HBM right now mostly silicon interposer have been used, but there are attempts, there are designs going with organic. I don't have specific about HBM, but other 2.5D systems are there. The minimum feature sizes and have to improve a bit more on this way, right? So that is some of the key requirements which will probably be coming up, and it could be resolved. I see there are several attempts of doing organic and also trying new stuff.
Okay, great. So, one last question is like we are separating HBM3, the CK and the DQS line, right? So there is obviously like there is, the command has to go along with your data line so that after certain cycles it has to come back. So there is always something we do read leveling, write leveling, and we do the DQS CK leveling and so forth, right? So how does that's been kind of taken care, by completely separating it out, CK and DQS, right? Can you throw more insight about it, how it's been done in HBM3?
Okay, I can take that one. Um, so from the consortium of HBM3, what we have is what has been given is a method to actually do the alignment training as a sequence.
Okay.
Right. So to make sure that the right strobe and the clock are kind of aligned to within their limit. Now beyond that, whatever like you mentioned, levelization. So I guess the idea is that everyone comes up with their own scheme. So it's all like whoever wants to use whatever method, they can come up with that and do the levelization. But yes, the need for levelization is definitely there. That is definitely a very pronounced thing. So yeah, I mean everyone has their own way of doing that. But yes, you're absolutely right. Both on the read path as well as on the write path, levelization is necessary because of this misalignment.
Right. So on point of view of the design community, I have this question. Maybe Manish have touched based on the SAPA aspects of it, right? Because the more the data bit or more that you pump in your data rates into it, the SAPA is always going to be the challenging aspects of it. If let's say the design community, when they try to adopt to HBM3, what are the few considerations that they have to take care during the integration of the files, and as well as designing the package and the boards? Maybe a couple of cents from you both of the experts.
Sure. I think there's very important and valid questions about SIPI, and we have seen some of the systems in HBM early generations when it was not taken care. Even it was running at lower data rate like 2 Gbps or 3.2 Gbps, not hitting the actual speeds they were designed for.
Right.
So Interposer design has to be taken as a full SI challenge, and it has to be properly reviewed. The timing, voltage timing budgeting is important. So all component budgets and IMASC and have to be taken care. So it is how you partition your system margins that is important.
Right.
We have seen crosstalk being an important factor in the design. So it has to be, and there is no cross cancellation scheme which can be done for such a small form factor things. So that is very important. So that needs to be taken care. So basically, silicon interposer has to be really looked at in the layout. There are many effects which can go hidden. The other thing which is very challenging here is extracting the interposer. So there are tools available, but what portion of your segment you are taking up for the extraction and modeling, that is key. Because if we take too narrow of a portion, we may miss out some of the parasitics and some of the things will, some of the signals will show better results than they actually are in the silicon.
Right. Yeah, I think well said. I think the right budgeting and executing and probably doing in thorough SAP simulations are going to be very vital in moving forward, right? Yeah, it's excellent. I think by which I think I would like to conclude the presentation with heartfelt thanks from VLSID community, and thanks for sharing all your insights. Thank you, Nikhil and Manish.
Thank you, Dana, Dr. Shah, and all the audience.